Hello everybody, welcome back to the tutorial for measurements. Now let's look at question 10. In this question, we took the time for 15 oscillations of a simple pendulum, and now we're going to find out what is the value of the period time for one oscillation. So here is the time for 15 oscillations. T is equals to 27.4 plus minus 0.2 seconds. So in order to find the period of the oscillation, we must divide the time for 15 oscillations by 15. So we take 27.4 divided by 15. Now, this doesn't give us a nice number, but we will round it to 1.83 seconds, which is 3 significant figures. The reason why we do this is because the data is also 3SF. What about the uncertainty in the period? The uncertainty in the period will be uncertainty of the time measurement divided by 15. In this case, it's 0.2 divided by 15. Now, once again, this is also not a nice number. It's a 0.013. But we need to round this up to 1/6 because all uncertainty, absolute uncertainties are rounded to 1/6. So all in all, the period can be represented by the the period is represented by the number 1.83 plus minus 0.01, and then we put a bracket here, seconds. So what about the percentage uncertainty in the period? The percentage uncertainty in the period will be the absolute uncertainty of the period divided by 1.83. Okay, and this will have 100% multiplied by, to convert it a fractional uncertainty to a percentage uncertainty, we have to multiply by 100%. And so this gives us 0.55%. Now, percentage uncertainties are always represented to two significant figures. So this is part A. Now let's take a look at part B. So the length of the pendulum as measured by a ruler is 82.2 plus minus 0.1 cm. Given that the period, which we calculated from before, over here, is given by 2 pi square root L over G, calculate G and its uncertainty delta G, and hence write the answer for G. Now, the most important thing to note for this question is that you must make G the subject of the formula before calculating the uncertainties. So let's rearrange this formula, okay, to make G the subject of the formula. First, we will square both sides of the equation. So you get T squared is equals to 4 pi L over G. Then we rearrange the formula by putting G on the left side and then putting T underneath. All right. So once we do this, we'll be able to work out the value for G by substituting in the equation. So the value of G, the basic value of G would be 4 pi squared multiplied by the length, which is 82.2 cm. So we'll change that to 0.822 meters divided by the period, which is 1.83 seconds squared. Sorry, this should be a square over here. So it's 1.83 squared. Now, when we work this out, we'll get a value of G of 9.690 meters per second squared. So we leave this in 4SF first because now we need to work out the uncertainty of G. Now, because of the multiplication rule, we need to work out first the fractional uncertainty of G. We see that there are actually two variables that are used to calculate G, which is L and T squared. So the fractional uncertainty of G will be made up of the fractional uncertainty of L plus, because T squared means that there's actually two T's inside here, so there will be 2 times of the fractional uncertainty of T. So let's put this into the formula. The fractional uncertainty of L is actually 0.1 cm over 82.2 cm. You notice that it's okay to express it in centimeters here because it's just a ratio. Then over here, 2 times of 0.01 divided by 1.83. Remember, this number was obtained from our previous question over here. Right, so this works out. You don't have to work this out straight away. okay, we can put in delta G is equals to G multiplied by 0.1 over 82.2 plus 2 times of 0.01 over 1.83. Now, what value of G do we use? We use this value of G over here. So delta G will be equals to 9.690. Of course, I'm writing out all the working, which I encourage you to do that. But if you are short of time, you can just put it straight in your calculator. So this step must be shown, okay, show this step to get the marks, to get the M1 mark. So M1 mark requires all the numbers to be shown. Okay, you need to substitute, show that all the numbers are substituted in order to get your M1 mark. If not, you will not get the mark. So the actual working out alone is not required. Is 0.1 meters per second squared to 1 SL. Okay, so then in that case, therefore, G itself will be equals to 9.7 plus minus 0.1 meters per second squared. So that is the answer for question 10. Now let's take a look at question 11. Before we do question 11, I'm going to show you what is the wrong method. Okay, so we're given the formula, the length equation formula, 1 over u plus 1 over v equals 1 over f. What is the uncertainty of focal length f? Now some of you may be tempted to do this, equals to 1 over f, and then we do u plus v over uv is equals to 1 over f. So f is equals to uv over u plus v. Then we say that delta f over f is equals to delta uv over uv plus something like that. So it's going to be a very complicated formula. Now this formula will not work because the terms here, okay, we did not separate out the variables u and v, okay, appear in both terms, in both of these terms here, both sides. That means that the uncertainty in f is not made up of u or v, but a combination of the two. So in this case, we won't be able to find the uncertainty using this method. So for complicated formulas, max best method is the safest to use. So now what we can do is that we can try to work out the maximum value of f. Okay, so we try to work out the maximum value of 1 over f over here. So we say, what if u and v are both very large? Okay, so we try number 1. We say 1 over f is equals to 1 over u. The largest value of u will be 53. And then the 1 over v, the largest value of v will be 205. Now this gives us a value of f of 42.11 mm. Now we can try again, right? Try number 2, but this time we put in all the smallest numbers, 1 over 47 plus 1 over 195. And this gives us a value of f, which is 37.87 mm. Okay, so and then in this case, the uncertainty of the focal length f will be f max minus f minimum divided by 2, which is 2.12 mm. So notice that the question actually put the uncertainty to 2SF. Well, that is something that is not encouraged. Okay, so this is the best answer of the MCQ. Please don't do this in your actual structured question. We cannot leave it to 2SF. Okay, it should be 1SF normally. All right. So this is question 11. All right, let's take a look at question 12. Now this question gives us a very unusual formula that we have never seen before, but don't worry, we can always analyze uncertainty questions easily. Right. Now there are two concepts in play here. First of all, rearrange the equation before starting the uncertainty calculation. And next, you see this term v over t. Now don't try to split it up into v and t. Instead, you use it as a single object. Okay, so now our intention of this question is to express the value of the viscosity eta and its associated uncertainty. So we can see that we can rearrange eta in the formula by exchanging it with the term V over T like so. Eta is equals to pi E R4 over 8L V over T. You'll notice here that I left V over T inside here because it is a single measurement and I don't want to kind of break it up into T over V because that will mess up everything. Right, so first of all, we'll do the best guess measurement of eta first. So we'll put it over here. I'll fill in all the values, okay? Sorry, what I meant was that the value of eta is already known. It's given to us as 1.137 times 10 to the power of minus 3. Okay, so eta is given over here. Now what we need to do is to find the uncertainty in the value of eta. Now, we will use the multiplication rule to find the uncertainty in the value of eta. You'll notice that all of the uncertainties are given in percentages. So what we can write is that the percentage uncertainty of eta will be the percentage uncertainty of the fractional uncertainty of eta will be the fractional uncertainty of the measurements that make up eta. Now, how many measurements are there? There's P, there's L, there's R, and there's V over T. But R is to the power of 4. So it contributes 4 times of the percentage uncertainty. L, although it's in the denominator, it's a plus to the percentage uncertainty. And then, of course, we have the percentage uncertainty of V over T, which is treated as a single measurement. So the percentage uncertainty of eta will then be the percentage uncertainty of P. Percentage uncertainty is 2% plus 4 times of the percentage uncertainty of R. The percentage uncertainty of R is 2.5%, right? And then we add the percentage uncertainty of L, which is 0.5%. And then we add the percentage uncertainty of V over T, which is 3%. And this gives us a grand total of 15.5%. Now, we'll leave this in 3SF for the time being because it's intermediate working. So we'll just leave it as an intermediate 3SF. Okay, you can also change it to 2SF, okay, if you want later on. Now, so how do we find the percentage, the absolute uncertainty of eta? Now, the absolute uncertainty of eta will be eta multiplied by this 15.5%. So we'll take 1.137 times 10 to the power of minus 3 times 15.5%. Okay, and that will give us a value of 0.2 times 10 to the power of minus 3. Okay, so now we can express eta as a value plus the uncertainty. Now we notice that the value is given to 10 to the minus 3 and uncertainty is also 10 to the minus 3. So I think what I'll do is that I'll move the 10 to the minus 3 out of the box, okay, times 10 to the minus 3, and then I'll fill in the value of the units which was given to us in the question. Okay, now we notice that over here, the decimal place is incorrect. Okay, so the uncertainty is given to 1 dp, but the actual number is given to 3 dp. So we got to cancel these two away, and now we got a correct answer, okay, over here. Now, if you take a look, which is the measurement that contributes the most to the percentage uncertainty? I'll look over here. The measurement that contributes the most to the percentage uncertainty is R. Since R appears as R to the power of 4, so its percentage uncertainty is also quadrupled, and also it's not a small percentage uncertainty. It's quite large actually. Now, a 16% percentage uncertainty in your measurement is actually pretty bad. Normally, we try to aim for anything less than 5% or 10% for a school experiment. Okay, in university, the measurement I think should be less than 1% uncertain, even better than that. So that's the end of this question. Now let's take a look at question 13. For question 13, the main concept is resolving forces along a slope. Now let me take you on a tour of what forces there are along the slope, and this must be memorized. Okay, sorry, there's no way to do this quickly during an exam. So what we have here is a slope, okay, and the slope angle to the horizontal is given as theta. Now if we have a block over here, we'll see that the block is stationary over here. So this block is stationary. And so there are several forces acting on the block. The first force acting on the block will be the weight. The next force acting on the block will be the normal contact force. And the last force acting on the block will be the friction, which we call small f. Okay, now it's not easy to analyze the forces acting on the block because everything is at an angle. So what we're going to do is we're going to resolve the weight into two directions. The two directions that we're going to resolve the weight will be parallel to the slope and perpendicular to the slope. Okay, now this how we're going to do this is that we're actually going to draw, okay, the angle theta, all right, in several you have to watch carefully because this angle theta is going to be quite difficult to place. Now you notice that theta is the angle between the slope and the horizontal. So the angle between the slope and the horizontal angle is theta. Now using the property of opposite angles, all right, this angle is also theta. Okay, now however, what about the vertical side? Now using the property of angles, okay, this angle is actually theta. Oops, what did I write? This angle is actually theta, and over here this angle is actually theta. All right, theta. So you can see the theta actually, the angle theta actually forms kind of like a windmill. Okay, so this is the vertical and this is the horizontal. Okay, so I would say this is like my windmill theory, okay, of theta. Okay, so every time you try to find theta, all right, when the slope goes up a little bit like that, this is theta. That means the vertical, this is theta. So this is the windmill effect. Okay, so if I do my hands really fast, can you see the theta angle start to appear? Okay, never mind. If you can't see it, then in the comfort of your own home, can you please go and try? Okay, so over here now, so let's take a look again at the weight. So this is the weight, okay, and this is the windmill theta, which was okay, which we got over here. Now, so the weight can then be resolved into two components, one pulling down the slope like this, one pulling down the slope. Okay, down the slope, since this is theta, this will be the sine of theta. So this will be W sine theta. W sine theta. And the weight is also pulling into the slope in this direction. The weight is pulling into the slope. Since this is theta, this will be the cos theta. So this is W cos theta. So over here, this is W cos theta. So now we can remove the W, okay, and this is what you need to memorize. You need to memorize the following rule, and how you remember it is like this. Remember this, weight down slope is W sine theta, okay? Trust me, you must memorize it because I don't want to see you guys in an exam doing a windmill, okay? You certainly don't have any time to do that. Okay, so remember, weight down slope is W sine theta. And if the weight down slope is W sine theta, then the weight perpendicular to the slope must be W cos theta. Now, this leads us to realize that if the block is stationary, then the normal force must be also equal to W cos theta, since the normal force must balance with the weight into the slope. And ta-da, you know that the friction force must be equal to W sine theta, since the friction force for a stationary block must be equal, okay, to the weight pulling down slope. So just by drawing this simple diagram, okay, and remembering that the weight down slope is W sine theta, then the weight into the slope will be W cos theta, the normal force will be W cos theta, and if the block is stationary, then the friction, or if the block is at equilibrium, the friction is also equal to W sine theta. Of course, the friction is not always equal to W sine theta, so the block actually can slide downhill. Okay, so let's take a look. The box of weight 300 Newton is placed on a slope as shown below. Determine the component of the weight of the box along the slope and perpendicular to the slope. So the answer to this is quite clear. Okay, so the weight down slope is 300 sine 30 is 150 newtons, and the weight perpendicular to the slope is 260 newtons. Now, it's a good idea to draw the forces into the diagram so that the teacher can see which direction your forces are. Now, how do you resolve forces? The first thing you do is to draw a parallelogram. Okay, and then after that, using a ruler, draw the resolved forces with two arrowheads. All right, then you put down 150 newtons and 260 newtons. So this will resolve all ambiguities, and the teacher will know that you know what they're talking about. Okay, that's the end of question 13. Now let's take a look at question 14. For question 14, it's not going to be possible to use our into the slope and stuff like that, because this is not the weight anymore. This is a horizontal force that is applied. So we're going to resolve this horizontal force along the slope and perpendicular to the slope. So the first thing we do is that we will draw the 100 newtons. Make sure to draw a very nice big nice and big force so that we don't draw a small force, okay, because we have a lot of space, so we try to draw as big as we can. And then we draw our windmill. Okay, we're going to start to draw our windmill. All right, now this angle over here is 25 degrees, so by the alternate angle theorem, this is also 25 degrees. Okay, so how are we going to resolve this force into the along the slope and down the slope components? The first thing we do is to draw a parallelogram. Which I've drawn very badly. Okay, we draw a parallelogram that for which the force is the diagonal. Then starting from the same point, we draw two components, one this way, okay, and then the other one can be this way, and we end up at the same point, so that if you follow the double-headed arrow, you go up and then you go down, it ends up as the same point as the 100 Newton force. That's how you will know that you have resolved it correctly. Now let's take a look. This angle is touching this side and this side, so this must be a cosine of the 25. Now this side here is not touching the angle, so it must be the sine of the 25. So in this case, this would be 100 sine 25, and this would be 100 cos 25. Okay, oops. So let's solve the problem over here. The component of the 100 Newton force along the slope will be 100 cos 25, which will be 90.6 newtons, and into the slope perpendicular will be 100 sine 25, and this will give us 42.3 newtons. Now once again, it is a good idea to draw the components of the force. Okay, now when we draw the components of the force, the first thing that we'll do is that we'll draw a parallelogram. So we're going to draw a parallelogram once again, okay, that is parallel to the slope, which is very badly drawn by myself. So I'm going to erase it and try again. All right, parallelogram. Use a ruler, please. Okay, so over here, this is the component of 90.6 newtons, and this component over here will be 42.3 newtons. Try to be as neat as possible because the teachers do value neatness. So that's the end of question 14. Okay, let's take a look at question 15, the change of velocity. Now, I'm first going to show you the wrong answer, which many students do this. Okay, so a car changes its velocity. So usually people will draw a car, okay, and the car is traveling due east. So people will draw the car traveling due east like this, okay. So the car is traveling due east at 30 meters per second, and then what will happen is that the people will draw the car over here. All right, then the car changes its velocity to 25 meters per second due south, and then people will say that, oh, so therefore this is the change of velocity. Now this is wrong. Okay, now velocity is always drawn assuming that the object, from the object's point of view, they're assuming that the object is stationary. In this case, what the student did wrong is that he drew the velocity on the ground instead. Now, what he didn't actually draw the velocity of the car. What he actually drew is the displacement of the car instead of the velocity. This is actually the path that the car traveled, all right, as it moved east and then due south. Now, so how should you draw the velocity diagram? So how I usually draw the velocity diagram is that I will draw the car stationary first, like a box. So its initial velocity, v1, is 30 meters per second due east. Its final velocity, okay, v2, is 25 meters per second due south. Then I'll take the original velocity and pull it down to the new velocity. This is a change of velocity. So the change of velocity is how you pull the original velocity to the new velocity. Okay, now, so how do we calculate the change in velocity? That's quite easy. The change in velocity is actually just the Pythagoras theorem, but we need actually to find the direction of the change of velocity as well. So the change of velocity, the easiest way is to give the compass bearing of the change of velocity. Okay, since the um, the question gives us east and south. Okay, but in any case, let's start with the calculation. So we'll begin with the magnitude of the change of velocity. The magnitude of the change of the velocity will be the square root of the magnitude of the initial velocity squared plus the square of the magnitude of the final velocity. So this is 30 squared plus 25 squared. So the magnitude of the change of velocity will be 39 meters per second. Now let's try to find the angle over here. This angle theta. Okay, so theta will be equals to the arctan, okay, of the magnitude of the velocity v2 divided by v1, 35 to 30 degrees. So this will be about 40 degrees. So therefore, we can write the change of velocity is 39 meters per second, right? And then we can do this compass bearing, which is 270 minus 40, that is 230 degrees, okay, at bearing 230 degrees. Or you can write 40 degrees south of west, or well, I guess that's probably the easiest way to answer the problem. Now, so calculate the change in the speed. Now, change in speed is just the difference in the magnitudes of the velocity. The final velocity minus the initial velocity magnitude. So that will be 25 minus 30. And the change in speed will be negative 5 meters per second. Now, the wrong answer, of course, if you put 5 meters per second, if you put positive 5 meters per second, that is wrong since the speed itself is decreasing. Okay, so this is question 15. Now let's take a look at question 16. In question 16, the main concept that we learn here is to how to resolve into vertical and horizontal components. Right, so that's our main concept for this question. Now, how are we going to resolve into vertical and horizontal components? Let's try the 5 Newton force first. You can see the 5 Newton force is going to the right over here, and then it's going upwards. Now, since this angle is touching this side, this must be a cosine 30 degrees. Right, so this is 5 cos 30. And since this side here is not touching the angle, this must be a sine 30. So this is 5 sine 30. Now let's do the same for this one. This one is going down and then to the left. Going down and then to the left. Okay, so this side over here is touching the angle. So this is a cos 10 degrees. So this is 8 cos 10. And this side over here is not touching the angle. So this would be 8 sine 10 degrees. Now, so what we can actually do is that we can actually list out the forces as a x and y vector. So the forces x and y vector, okay, for the 5 Newton force is actually, this is the x vector, so it's actually going to the right 5 cos 30 and going up 5 sin 30. So we can write 5 cos 30 and then 5 sin 30. Okay, now this vector is going down and to the left. And you know that going down is always negative. So what we can write is that we can write, going to the left, all right, the x vector is minus 8 sin 10. And then over here, this is 8 cos 10, right? So we are minus 8 cos 10. All right, so we work it out on a calculator, all right, to get the resultant vector. And punching it into the calculator, we'll get a vector that looks like this, 2.94 and negative 5.38. So let's draw this vector. This vector is going to look like this, 2.94 to the right and negative 5.38, okay, to downwards. So that means that when these two vectors add up, this is the result. Now we need to actually put it back into a single vector again. We need to put it back into a single vector again. So what we can write is that the resultant force is equals to 2.94 and minus 5.38 newtons in the x and y direction. So the magnitude will be equals to the square root of 2.94 squared plus 5.38 squared. Okay, so the magnitude that we are given is 6.13 newtons. Now we need to write the direction over here. So we write down an angle theta over here, and we can write theta equals to arctan, and we arctan the side 5.38 over 2.94, which gives us 61.3 degrees. So finally, we can write the resultant force is 6.13 newtons, 61.3 degrees, okay, clockwise below the horizontal as shown. Right, so we write down as shown because it's difficult to explain in words. It's easier to explain in a diagram. Okay, so this is how I would do this question by using the vectors. And let's take a look at question 17. Question 17 is a relative velocity problem. A car and a bicycle are equal distance from the crossroads. The car is traveling north with a speed of 15 meters per second and the bicycle is traveling east with a speed of 5 meters per second. At this instant, which arrow represents the velocity of the bicycle relative to the car? Now, the concept for relative velocity is simple. We must find out where is the observer first. In this case, relative to the car tells you that the observer is inside the car. So, when you're in a car, that means now you are in the car, okay? And then you are looking at the bicycle. So now we need to find the bicycle's velocity relative to you. So imagine you're driving down the road in the car and you're coming to a traffic junction and you see a bicycle crossing from your left to your right. So how is the bicycle moving relative to you? In order to do this using vectors, we can subtract the observer's velocity from the target's velocity. Okay, so what we're going to do is that first we're going to have the bicycle. Okay, this is the bicycle, and the bicycle's velocity is 5 meters per second to the right. Now we're going to remove away, subtract away, okay, the car's velocity by adding the reverse vector. Okay, this is 15. So this is how the bicycle will appear to move. This is the relative velocity. Okay, so what happens is that the bicycle is going to appear to come towards the car, all right, in that direction. I hope it doesn't crash. Okay, so which arrow represents the velocity of the bicycle relative to the car. Now we have two possibilities, A and C. Both of them are moving in the same general direction. But take a look at the relative length of this guy. This is 5 and this is 15. So definitely C must be the answer because A doesn't look like it's got the right proportions. Okay, so this is question 17. And with that, I think we are done. The next part will be the additional questions, which I encourage you to do on your own. Thank you for listening and have a nice day.